Hi, I'm Zor. Welcome to Unizor Education. I'd like to talk about another example of a sequence, relatively simple example. It's called geometric sequence or geometric progression. In a way, it's somehow analogous to arithmetic progression. It's different, but there is some analogy which you can imagine. So the previous lecture was about arithmetic progression, and this one would be about geometric progression. So let me start with a definition. What is a geometric progression? First, you have to choose the first element. And you also have to choose something which is called a quotient, or a factor, or a multiplier. Now, all other elements of this sequence are formed sequentially, starting from 1, by multiplying by this quotient. So the number 2 would be a times q. Number 3 would be a times q, which is a q squared. So you remember that arithmetic progression was adding the same number. Now, geometric progression is multiplying by the same number. Well, obviously, there are some trivial cases, like for instance, what if q is equal to 0? Well, you will get a, and then you will get 0, 0, 0, 0. Trivial fact. It's kind of geometric progression, but very non-interesting. Now, another also trivial case is when the q is equal to 1. So you will have a times 1, which is a times 1 times 1, which is still a, so it will be a, so the whole geometric progression would contain the same element repeated many times. So not interesting. So we will probably assume, whatever I will be talking about, I will assume that q is not equal to 0 and not equal to 1. And quite frankly, I don't think it's very interesting if you will put q equals to minus 1, because if q is equal to minus 1, you will have a, and then minus a, and then a, and then minus a. Again, it's not really, changing. It's just two values jumping left and right, a minus a, a minus a. Trivial case. So these would probably be some kind of, it's not really a restriction, it's just something which I don't want to consider, quite frankly, because it's very trivial. Now, let's talk about the nth element of this particular progression. Well, as you have probably figured it out, to reach the nth element, I have to multiply a by q 1, 2, 3, 4, n minus 1 times, right? To get to the number 2, I have to multiply y 1 times, once. To get to number 3, I have to multiply a by q 2 times, and to get the number n, I have to multiply a by q n minus 1 times. So this is supposed to be the formula. Now, again, how can we prove it? Again, by induction, obviously. Well, what are the characteristic properties of geometric progression? Element number 1 is a, so let's substitute n is equal to 1 here. You will have n, which is equal to 1 minus 1, 0, q to the power of 0 is 1, so you will have a, obviously. So that's fine. Number 2 is that subsequent element is equal to the previous multiplied by q. Well, indeed, if you will multiply a q n minus 1 by q, you will get a q to the nth degree, and formula for n plus 1 is basically a times q. If this is n plus 1 minus 1, so it's n. So it's the same thing. So the property is checked, which means basically we have proven that this is the formula for nth element of geometric progression. Now, I would like to analyze how values of geometric progression, how elements are changing basically as the n grows to infinity. Now, if you remember from the previous lecture about arithmetic progression, we basically proved that for difference of arithmetic progression positive, we go to the positive infinity, unrestricted basically. So no matter what kind of a boundary we put ourselves, we will always overcome that boundary and will move forward, being bigger and bigger and bigger. For negative d, it's correspondingly to the left, which means we are getting smaller and smaller numbers going to minus infinity. Now, what about geometric progression? Is it more or less the same? Well, yes and no. Actually, if you consider arithmetic progression, let's talk about the positive difference, d. It's always growing. No matter what's the value of d, if it's 1/2, or if it's 25, or if it's a million, we are always moving forward sequentially, step by step, and eventually we will definitely overcome any boundaries. In case of geometric progression, that's not exactly the case. Let's consider the positive quotient q. Is it always increasing the absolute value of initial number a? Well, if q is greater than 1, then answer is yes, right? When do we increase? Well, again, considering q, let's just consider a is positive. If a is positive, then we basically divide both sides of inequality by a, and we get q is greater than 1. So if q is equal to 1, then aq is greater than a, which means our elements are becoming bigger and bigger and bigger. So let's just consider, for simplicity, positive a and positive q, so I don't have to talk about absolute value, etc. So for positive a and positive q, if q is greater than 1, we are increasing values. What if q is less than 1? Then obviously the sign of this inequality would be different, because whenever we multiply something by less than 1, positive numbers, we will get smaller number. Whenever you multiply 25 by 1/2, well, you will have 12.5, which is smaller. So it looks like for geometric progression, there are two cases. In some cases, the geometric progression is growing, and growing indefinitely, basically, in absolute value, or if we consider only positive a and q, you can just say in values. It grows to the positive infinity. But for other q's, which are less than 1, still positive, the situation is different. The values are decreasing. So basically, this is the property which I would like to talk about and quantify it. We would like to find out when exactly, same as we did for arithmetic progression, when exactly we will become greater than any number or smaller than any number. And again, let me just assume right now that this is the general formula for geometric progression, and let's assume these three things. So the positive first member, the positive quotient, and the quotient is not equal to 1. Now we have two cases, from 0 to 1, and then from 1 and more to infinity, basically, greater than 1. Two cases. All right, so let's do the first one. If q is from 0 to 1. So I don't need to remove this. So this is my first case. Now, this is when I'm saying that numbers are decreasing. They're smaller and smaller and smaller. So if you take, for instance, this is 0, this is a, and you multiply it by q the first time, you get smaller. Let's say you multiply by 1/2. You multiply by 1/2 again, you will have even smaller and smaller, etc., etc. And eventually it will become smaller than any number, whatever the number I choose, z. It will become smaller than this number z. 1 millionth, 1 quadrillionth, whatever it is. If q is less than 1, eventually it will be smaller. Well, let's check how it behaves, and let's find out the number n in this sequence when it will become smaller than z. So we assume that z is any number, again, in this particular interval. It's somewhere here. And I'm looking for the case when my general member of geometric progression becomes less than z. I mean, obviously, if z is greater than 1, I don't really need this restriction, because obviously if z is greater than 1, it will be the same formula. All right, so what can we do to solve this particular inequality for n? Well, obviously the first thing is we divide by positive a to get this. All right. Secondly, we apply decimal logarithm to both sides, and obviously it will be and now, what is log a? Log q, sorry. Q is from 0 to 1. And let me remind you the graph of function y equals log x. If x is from 0 to 1, logarithm is negative. If x is greater than 1, logarithm is positive. Well, if you forgot properties of logarithm and the fact that logarithm of a power is the power multiplied by the logarithm, you just have to repeat this from other lectures in algebra or internet, wherever. Okay, so basically log q is negative, considering q is from 0 to 1, which means if I divide both sides of inequality by log q, my sign should be reversed. So I will get n minus 1 greater than log z over a divided by log q. And as a result, we get add 1 to both sides. So n should be greater than 1 plus log z over a divided by log q. So that's the formula. It gives me the sequence number n, after which my geometric progression is smaller than any number z, wherever the z is, chosen. Okay, now let's consider a different case, when q is greater than 1. So here we can say that a q n minus 1 would be smaller than z. and obviously greater than 0 because everything is positive here. All right, fine. Now let's consider the case when q is greater than 1 and start doing exactly the same thing. We would like to find out when our element of geometric progression becomes greater than z. Okay, the first manipulation, divide by a both sides. A is positive, so inequality, retains the sign. Now we do the same thing again, logarithm. Logarithm is monotonously increasing function, which means if this is greater than this, the logarithm of this would be greater than logarithm of this. So the logarithm of q to the n minus 1 would be n minus 1 log q greater than log z over a. Now log q is positive, because again, if you remember the same graph, for q greater than 1, the logarithm is positive. So you divide by positive number left and right parts of inequality, retaining the inequality sign. So it remains greater. N minus 1 greater than log z over a divided by log q. And as a formula, we have exactly the same thing as you see. N greater than 1 plus log z over a divided by log q. And in this case, would be greater than z. So if n is greater than this number, then members of our progression will be greater than z. So this is kind of a border for sequence numbers. Any number with the number greater, any number with a value greater than this would deliver the elements of our geometric sequence greater than z. And obviously all subsequent will be greater as well. In this case, all subsequent will be smaller as well, because we are multiplying by quotient q, which is positive quotient, but it's less than 1. So we are decreasing the value, the positive value. Now, I deliberately did not consider cases when a is negative or q is negative. They are basically exactly the same thing, except you can always talk about, instead of increasing to positive infinity, you will be decreasing to negative infinity. Instead of decreasing to 0 from the positive side, you will have increasing to 0 from the negative side. So from the absolute value standpoint, these two cases are exactly equivalent to each other. That's it for geometric progression. I will also talk about some of elements of the geometric progression when I will talk about series. That will be another lecture. Meanwhile, there are a few problems on the internet on unizor.com which are dedicated to sequences. Please try to solve them yourself and then go to lecture which is explaining basically what these solutions are. I am encouraging all the parents actually to take part in working with this particular website with their student, with their children, or whoever they supervise. It allows you to control the educational process. It allows students to take exams, and for you, the parents, it allows you to basically make a judgment about how well your student really studied this particular material. And considering you can repeat as many times as you want any lecture or any exercise, any problem solving technique, whatever. So just repeat whatever you don't feel comfortable with and you'll be fine. Thanks very much. That's it for today.